Time feels constant in our everyday lives. Seconds pass one after another, clocks tick at a steady rhythm, and the flow of time seems the same for everyone. But modern physics has revealed that this sense of uniform time is an illusion. Time is not fixed. It can stretch, slow down, and even behave differently depending on where you are and how fast you are moving. One of the most extreme places where this happens is near a black hole. To understand why time changes near a black hole, we need to look at Einstein's theory of general relativity. According to this theory, gravity is not simply a force pulling objects together. Instead, gravity is a result of mass bending the fabric of space and time, often referred to as spacetime. Imagine placing a heavy object on a stretched sheet. The sheet curves around the object, and smaller objects moving nearby will follow curved paths. In a similar way, massive objects like stars and planets curve space-time, and other objects move along those curves. Black holes represent the most extreme version of this effect. They form when massive stars collapse under their own gravity, compressing an enormous amount of mass into an incredibly small region. The result is a gravitational field so intense that it dramatically distorts both space and time. As you move closer to a black hole, the curvature of space-time becomes stronger and stronger. This leads to a phenomenon known as gravitational time dilation. Time passes more slowly in stronger gravitational fields. This is not just a theoretical idea. It has been confirmed through experiments. For example, clocks placed on satellites orbiting Earth tick slightly faster than clocks on the surface because they are farther from Earth's gravitational pull. Even these tiny differences must be corrected for systems like GPS to function accurately. Near a black hole, however, the effect becomes extreme. Imagine two observers. One remains far away from the black hole, while the other travels toward it. Each observer carries a clock. From a perspective of the distant observer, the clock near the black hole appears to tick more slowly. As the traveler approaches the event horizon, the boundary beyond which nothing can escape, this effect becomes increasingly dramatic. The clock seems to slow down more and more, as if time itself is stretching. At the event horizon, from the distant observer perspective, time appears to almost stop completely. The traveler never seems to cross the boundary. Instead, they appear frozen in place. Their image becoming dimmer and redder as the light they emit loses energy while escaping the black hole's gravity. This effect is known as gravitational redshift. Light, leaving a strong gravitational field, is stretched to longer wavelengths, shifting toward the red end of the spectrum. Over time, the traveler appears to fade away, as if they are slowly disappearing from the universe. However, this is only what the distant observer sees. From the traveler's own perspective, something very different happens. Their clock continues to tick normally. They do not feel time slowing down. As they approach the event horizon, nothing special seems to happen at that exact boundary. If the black hole is large enough, they might not even feel strong tidal forces at first. They would cross the event horizon without noticing any sudden change. This difference between perspectives highlights one of the most important aspects of relativity. Time is not absolute. It depends on the observer. Two observers can experience time differently depending on their motion and the gravitational field they are in. This leads to some astonishing possibilities. In theory, a traveler could approach a black hole, spend a short amount of time near it, and then return to a distant location to find that far more time has passed there. This is sometimes referred to as a form of time travel into the future. While such journeys would be extremely dangerous and difficult, the underlying physics is real. As we move closer to the black hole, the behavior of space-time becomes even more extreme. Near the event horizon, the distortion of space-time is so strong that it affects not only time, but also space itself. Objects falling toward the black hole are stretched in a process known as spaghettification. The difference in gravitational force between the near side and far side of an object becomes so large that it is pulled apart into long, thin shapes. For smaller black holes, this effect would occur before reaching the event horizon, making it impossible for anything to survive the journey. For larger black holes, however, the tidal forces at the event horizon may be weaker, allowing an object to cross the boundary before being torn apart deeper inside. Once inside the event horizon, the nature of space-time changes in a way that is difficult to fully comprehend. In some descriptions of relativity, the roles of space and time effectively switch. Moving toward the center of the black hole becomes unavoidable, just as moving forward in time is unavoidable in everyday life. No matter what direction you try to move, you are inevitably drawn toward the singularity at the center. The singularity is a point where density becomes infinite and the known laws of physics break down. What happens to time at the singularity is one of the greatest mysteries in science. Some theories suggest that time may come to an end there, while others propose that new physics may emerge beyond our current understanding. Black holes also raise deep questions about the nature of information and the fundamental laws of the universe. According to quantum mechanics, information cannot be destroyed, yet black holes appear to absorb everything that falls into them, potentially erasing all information about the original objects. This leads to the black hole information paradox, a problem that has puzzled physicists for decades. Recent theories suggest that information may be encoded on the surface of the event horizon or stored in subtle quantum effects, but a complete answer has not yet been found. The study of black holes is not just about understanding extreme objects in space. It is about understanding the nature of reality itself. Black holes push the limits of our theories and force us to confront the deepest questions about time, space, and existence. They show us that time is not a universal constant, but a flexible dimension shaped by gravity and motion. Near a black hole, time can slow to such an extent that an observer hovering just outside the event horizon could watch the distant universe evolve at an accelerated rate. Stars could form, galaxies could collide, and billions of years could pass elsewhere while only a short time passes for the observer. This idea reveals how dramatically time can differ depending on where you are in the universe. Even though black holes are distant and extreme, their existence has practical implications for our understanding of physics. The same principles that cause time dilation near black holes also affect satellites orbiting Earth and must be accounted for in modern technology. By studying black holes, scientists gain insight into the fundamental structure of space-time and the laws that govern the cosmos. Somewhere in the universe, near the edge of a black hole, time may be flowing so slowly that entire eras of cosmic history unfold elsewhere, while only moments pass locally. This strange reality challenges our intuition and reminds us that the universe operates according to rules that are far more complex and fascinating than our everyday experience suggests.